All right, team, you've finally arrived. You're going to be doing some real statistics from now on. So at this point, we have covered the basics of descriptive statistics and probability. And then we also have gone over how to use various distributions, whether they be discrete or continuous, to estimate probabilities. So now we're going to sort of put this all together and start making it more useful. And the first topic we're going to be discussing is the notion of a confidence interval, and in particular, using confidence intervals to help us estimate population proportions. So we learned all about the math behind population proportions, or the sampling distribution for population proportions, which we ultimately learned were provided the sample size was large enough that the sampling distribution was normally distributed, right? So we're going to be leaning on that pretty heavily in this section. So let's jump right in. So we're in section 9.1. So just to define some terms out the gate, we might hear or read the term a point estimate. So this is just another fancy word for a statistic, basically. So a point estimate is the value of a particular statistic. A point estimate is the value of a statistic that estimates a parameter. So statistics always correspond to parameters. Think X bar versus mu. Mu is your parameter, X bar is your statistic. A point estimate would be a specific value of X bar, right? So another example that's germane to this particular section is p hat. P hat is a point estimate for the population proportion, and a specific value for p hat would be given by X divided by lowercase n. This would be our point estimate for the population proportion P. All right, so let's jump right in to this notion of confidence intervals. So we learned about the population proportion, and what we learned is that the estimator, p hat, provided that the sample size was large enough and or the population from which we were sampling was already normally distributed. Provided either of those things or both of those things were true, then we knew that the sampling distribution for p hat was also normally distributed. So when we took samples out of the population and calculated the proportions from those samples, we found that those point estimates, those various proportions that we calculated for each given sample, they danced around the actual population proportion value. They never were necessarily exactly equal to P, but they were close to P. And we found that they clustered in a normal distributed way. So there was a lot of them that clustered around P and a few outliers that were in the tails of the distribution. So what we're doing with confidence intervals is the following. We take a sample and we calculate the population proportion for that sample, say sample 1. We then construct an interval that's centered at that value. So this value falls directly in the center of the interval. It has a lower bound and an upper bound. So we know that this p hat is close to, relatively speaking, it's close to P. So if we construct an interval that's centered at p hat, there is some likelihood that that interval will contain P. The wider the interval, the higher the likelihood that P, the actual value for the population proportion, will fall within that interval. So it's likely that we could construct a second interval for a second sample, and this second interval would be centered at the proportion for that second sample. And if we made the interval narrow enough, there's some likelihood that it would not contain P. So it can be really close to P, but we can construct a small enough interval around it that P would fall outside of that interval. So what confidence intervals are about is determining how wide must an interval be in order for us to assert with a certain level of confidence that the actual value of the population proportion will fall within the given interval. Okay, so what we're aiming to do is figure out what the fixed width of the interval needs to be, what the width needs to be, so that no matter what the sample proportion is, when I construct an interval centered at that sample proportion, I can say with a certain level of confidence that little p will fall within it. So it's totally possible that for a particular width of interval, we could still fall outside of, or that p could still fall outside of that interval. But if we make it wide enough, then that likelihood gets smaller and smaller. So what I'm trying to show you here is that I make an interval this wide, and you can see that if I scan it across the number line, that most of the time P will fall within that interval. And it's only in the case where I have really extreme values for P hat, which is the center of this interval, that I will actually lose P. So only for extreme values. However, if the interval was small enough, then I could have a lot of intervals that didn't contain P. You see that? So a confidence interval is all about figuring out what the fixed width of the interval needs to be so that you can say 95% of the time, if I construct an interval that's centered at P hat, it will contain P. There is some chance it may not contain P, but say 95% of the time it will. So that's what we're aiming to do. How do we figure out what this width of this interval needs to be so that we can say 90% of the time, 95% of the time, 99% of the time, when I construct an interval centered at some given P hat, it will contain the actual population proportion. Okay, so to say it in the textbook way, a confidence interval is an interval that's centered at P hat at some point estimate, where the width is such that we can assert with 1 minus alpha times 100% certainty that P lies within the interval. Okay, now this 1 minus alpha times 100%, I just threw that in here. We're going to deal with this quite a bit in this chapter. This is known as the level of confidence. What alpha is, we'll discuss shortly. It's called the significance level, but it doesn't matter right now. Just know that the level of confidence is the amount of certainty that we can have that if we construct an interval of a fixed width centered at a particular sample proportion value, that it will contain the population proportion. Okay, so this level of confidence could be 95%, 90%, 50%, whatever amount of confidence we want, but generally we want a high level of confidence. So we usually are dealing with 90 to 99% confidence. Okay, so let's take a closer look at what's going on here. So for population proportions, let's first just talk about how we would construct the interval that would have the right width that we need. Okay, so constructing the confidence interval centered at P hat with a certain level of confidence, 1 minus alpha times 100%. Okay, so think this actual value right here would be like 95%, 90%, something like that. The alpha is just whatever it needs to be in order to get us 95%, 90%. So you'll see that momentarily. So I'm going to give you the actual answer right out the gate. How do we construct the lower bound and the upper bound for the interval centered at p hat with a certain level of confidence? So the lower bound is p hat minus this thing called z sub alpha over 2 times the square root of p hat times 1 minus p hat over n. And that's the lower bound. And the upper bound is the same, except it's plus instead of minus. Okay, so both have a p hat, and then both have this same term here, the z alpha over 2 times this guy. But in either case, here we're subtracting it, and here we're adding it. So what are all these things? So of course, p hat is your point estimate. That's your sample proportion. Okay. This square root of p hat times 1 minus p hat divided by n, this is your standard deviation for your sample proportion, although it does look a wee bit different than what you're used to, because usually this is just a p, not a p hat. Now, the idea here is that this is actually not the that this is a estimator for the standard deviation of p hat. It's complicated. Don't worry about it. Just consider this your standard deviation. Okay. And then this last term, the z sub alpha over 2, this is a scaling factor that's drawn from a standard normal distribution that depends explicitly on the confidence level. So this is some number that scales the standard deviation such that when we subtract the standard deviation times that scaling factor and add the standard deviation times that scaling factor to the p hat value that's at the center of the interval, that we have the right width of interval to state with a certain level of confidence that our actual population proportion will fall within this interval. I know it's a lot of words, it gets kind of complicated. We're getting into some real statistics here. So just to give you a picture, again, you have your number line and then your interval that's centered at p hat and has a lower bound of p hat minus z alpha over 2 times the standard deviation, and an upper bound of p hat plus z alpha over 2 plus times the standard deviation. So this interval has a width, again, that has been constructed so that we have a certain level of confidence that if we go searching for p, that it's has some probability of falling within this interval. And that probability is the confidence level. So it may not fall within there, but if we make the confidence level high enough, there may only be a 1% chance that it doesn't fall within there, right? So a wide enough interval will mean that there's a much lesser chance of not containing p. Okay. So first, what is this z alpha over 2? It's sort of the elephant in the room. It's this weird thing that has been thrown in there. I said it was a scaling factor. Where does it come from and why do we need it? So without getting too complicated, let's just think of it this way. We know that p hat, provided we have the right criteria, we know that p hat is generally normally distributed. So if it's normally distributed, then we can use a z-score transformation to make it standard normal, which means if we transform it using the z-score formula, that it will then become a normally distributed, but with a mean of 0 and a standard deviation of 1. So now this z is distributed standard normal, so 0, 1. And if we look at the bell curve for the standard normal, then the Z alpha over 2 value is the Z-score for the value such that below that Z alpha over 2 and above minus Z alpha over 2, the area between those two values is exactly equal to your confidence level. So this red area right here is equal to the confidence level. And then the green area on the tails is half of alpha. Okay, so it's easier to think of this with numbers. So if I have a 95% confidence, then the red area is 95% of the distribution. 95% of the sample proportion values fall within this red area. So then it stands to reason that since the bell curve is symmetric, that the tails will then have 2.5% on one tail and 2.5% on the other tail, which adds up to 5%, giving us the complete 100%. So that's why it's alpha over 2, because we're cutting the remainder in half. This is the 95%. Alpha is the 5% that's left over, but we have to distribute that evenly between the two tails. So that's why it's alpha over 2. So the Z alpha over 2 is that particular Z-scores value that corresponds to the boundary between the middle area here, which goes with the confidence level, and the tails. So if you wanted to actually figure out for a certain confidence level what the Z alpha over 2 value is, you'd actually use your inverse norm function and put into the inverse norm function 1 minus alpha over 2. So just as an example, if the confidence level is 90%, then that implies alpha is 0.1, because it has to make up for it's the remainder, the leftovers from the confidence. And so the Z alpha over 2 would then be inverse norm of 1 minus 0.1 over 2. All right, getting a little glitchy here, sorry. So if you put that into your calculator, second vars inverse norm 1 minus 0.1 divided by 2, then that would give you a Z alpha over 2 value of 1.645. So it comes directly from the standard normal distribution. Notice that we didn't have to put in the mean or the standard deviation here, because we've already transformed this into a standard normal where the mean and standard deviation are 0 and 1 respectively, and the calculator defaults to the standard normal values, so we don't have to put them in for that case. So this is exactly what the Z alpha over 2 value would be. Okay, now since the confidence levels are fairly standard, we don't really need to calculate this every time. We can take it for granted. Okay, so you can calculate it if you wanted to, if you forget what it actually is, but you can commit this to memory. So the level, here are various levels of confidence for our intervals: 90%, 95%, and 99%. Here is the area in each tail. Remember that area is divided in 2, right? Because you have 2 tails. So if we have a 90% confidence level, then we have 0.05 in each tail, 0.05 area in each tail. And so That's the alpha over 2. That would, if we looked here, this is what I did it for the 90%, right? And this 0.1 divided by 2 is 0.05. So this is the value that we got when we use the inverse norm function, 1.645. Now, if we do this for each confidence level, 95%, 99%, then we get these different Z alpha over 2 values. So these are always the same values, no matter what. They don't change. They only depend on the confidence level. So you can write this on a sheet of paper and keep it on hand for when you're doing your calculations. You can commit it to memory, or you can use the inverse norm function to calculate it each time. It's up to you. So that's what Z alpha over 2 is all about. It's actually called the critical value. You can think of it, that's just terminology. So the Z alpha over 2, we call it the critical value. And you see where it comes from and why it exists. And you really don't have to rely on this terribly much to do the calculations. You can take all of this for granted. Okay, so finally, let's put it all together and just see what solving a problem with confidence intervals looks like. Okay, so in this example, 800 teenagers were asked if they use their cell phone while driving. 272 said yes. We want to attain a 95% confidence interval for the proportion that use their phone while driving. All right, so we're trying to construct a confidence interval. So we know that the confidence interval should be given by this. So all we have to do is figure out each one of these pieces and we got the confidence interval. All right, so P hat is X over N, and X is 272, and N is 800. So we put that in our calculator, 272 divided by 800, and we get 0.34. So that is our P hat value. All right, we need our Z alpha over 2 value. We have a 95% confidence. So we can do this with the calculator or use our table for a 95% confidence. Our Z alpha over 2 value is 1.96. Okay, and then finally, we need the standard deviation, which is P hat times 1 minus P hat all over lowercase n square rooted. So once we have P hat, we can do this. That's 0.34 times 1 minus 0.34 divided by 800. So we're going to put that into the calculator. Square root 0.34 times 1 minus 0.34 divided by 800. Oh, I did something wrong. Oh, forgot the decimal point. Okay. And so there we get a standard deviation of 0.0167. So I'm just gonna round it for these purposes, but it's better not to round. Remember, use the stored value in the calculator to do the computation. So now we have all the values we need to construct our confidence interval. We have the P, we have the Z alpha, the critical value, and we have the standard deviation. So lower bound for the interval is 0.34, which is P hat, minus Z alpha over 2, 196, times the standard deviation, 0.0167. So that's your lower bound for the interval. So you're going to put that in your calculator, 0.34 minus 1.96 times 0.0167. And that's 0.0167. 0.307. Okay. Then the upper bound, all the same values, just put a plus sign. So when you're putting your calculator, nothing easier. Second answer, scroll back, put a plus sign, and we get 0.373. Okay, so with these two values, we can see that the confidence interval is equal to 0.307 to 0.373. Okay, so how to interpret this confidence interval? So now we have the confidence interval. This is centered at p hat, right? So 0.34 falls right in the middle of it. And it has a 95% confidence. So what this means is that we are 95% sure that the actual value for the population proportion, P without the hat, we are 95% sure that that P falls somewhere within this interval. We don't know exactly where, but we know that with 95% certainty, with 95% confidence, that it's somewhere within that interval. It could be outside of that interval, but there's only a 5% chance that it's outside of this interval. That's a pretty small chance. So that's what this interval means. That's why it's useful. Okay. So there's a couple important observations to make about how these confidence intervals behave depending on how much confidence we are interested in having, and also the size of the sample that we're taking from the population. Okay, so in order to understand it, it's best to think in terms of what we call the margin of error. Okay, so the margin of error, big E, is really just that term in the confidence interval that we're adding and subtracting from p hat. So it has the critical value and the standard deviation multiplied together. So that's the term that we're subtracting and adding to p hat to construct the interval. And we call that the margin of error. So it stands to reason that depending on the size of the margin of error, that the interval will change size depending on how big or small the margin of error is. A larger margin of error means a wider interval. A smaller margin of error means a narrower interval. But the margin of error depends upon the confidence, which comes from the critical value, and it also depends upon the sample size. So we can see, really mathematically, we can see what happens with the Z alpha over 2 value increases with a larger confidence. And since it's it's directly multiplying, scaling the standard deviation, it stands to reason that the margin of error will get larger as we increase our confidence. So higher confidence means a larger confidence or a larger margin of error. So that makes sense. You know, if we make the interval wide enough, then we know that the population proportion value has a higher likelihood of falling in a wider interval than it does in a narrower interval. But it also means that we're introducing more error to our estimate. You know, a narrower interval means a stronger, more exacting estimate. So that's why we're calling it an error, because we're increasing the fuzziness of our estimate by widening the interval. So higher confidence means a larger margin of error. But there's also another ramification, which is that a larger sample size means a smaller margin of error. right? We can see that the sample size is in the denominator here. So the larger it gets, the larger the sample size gets, the smaller the standard deviation gets, and therefore the smaller the error gets. Now this makes sense intuitively as well, because we know that if we take a larger sample, that we'll get a better estimate of the population proportion. And we know this from the law of large numbers, right? Or the central limit theorem. As the sample size gets bigger and bigger and bigger, the sample distribution gets more and more normal and looks more and more like the actual distribution of the population. So higher confidence, larger margin of error, larger sample size, smaller margin of error. So since the margin of error depends upon the sample size, we can ask a corresponding question, which is, for a certain margin of error, what is the minimum sample size we need? So let's look at this example. Suppose you want to estimate a proportion with a 3% margin of error and a 95% confidence. How many individuals should be sampled? Okay, so let's start with the formula for the margin of error. And in fact, I'm going to make this even simpler and write it this way. No, never mind. I can't do it that way. So we start here. So we want to know, we know what E is and we know what Z alpha over 2 is, because those are specified here, the margin of error. And then the confidence, the 95% confidence directly determines the critical value here. So when we're told the confidence, we're effectively told the Z alpha over 2 value. So we know those values, right? And for a given sample, we can always compute p hat. So what we're trying to find is n. So what we're going to do is solve for n in this formula. Okay, so to do that, first I'm going to do the math here. We divide by Z alpha over 2. And I'm going to flip this around. Okay. And then we're trying to get the n out of the square root, so we're going to square both sides. That will kill the square root. Okay. Didn't quite give myself enough room here. All right. And now we want the n, but the n is down below. So the quick and easy way to deal with this is just flip everything over so that the n is on top. So if I flip it over, then I get here. And we're almost there. We almost have the n. I didn't quite give myself the room, but all we need to do now is take the denominator here and move it up. So just take everything in the denominator and bring it up to the other side. And so I'm going to flip over. You can follow along. But after I do that, I end up with n is equal to Z alpha over 2 over E squared times P hat times 1 minus P hat over, no, and that's just it. Sorry. So this is your formula. For a certain margin of error and a certain confidence level, this is how you would compute N. So in this problem, you'll notice that we weren't actually given a sample proportion. So when that happens, the best thing to assume is that p hat is 0.5. Okay. So if p hat is not given, okay, and this can happen, if it's not given, then that implies that p hat is 0.5. That's the best guess you can make. Okay, so then for us, we can finally solve that problem. What is the minimum number of people to sample? Well, that's going to be the Z alpha over 2 value for 95% confidence. Which again, we go to our table, 95% confidence. Critical value is 1.96. So 1.96 over the margin of error, which we told was 3%. So that's 0.03. That gets squared. And then we multiply by 0.5 times 1 minus 0.5. So put it all together. 1.96 divided by 0.03 squared times 0.5. And notice 0.5 times 1 minus 0.5. This is 0.5 times 0.5. So that's just 0.5 squared. And so we get a minimum sample size of 1,067, 0.111. So whenever you're dealing with sample sizes, you can't have a fraction of a person, right? So you always go up. Doesn't matter if you want, even though this would round down, we always go up. So the minimum value is 1,068. And this really should be stated as an inequality because any larger sample will also give us the same sort of, will give us at least that margin. Well, actually, no, I take that back. It's an equal sign because it's dependent upon the margin of error. So this is exactly this is exactly the end value that you need to get that certain margin of error. Okie dokie, this is a big section with a lot, and you're going to be using this stuff again and again. So you really need to chew on this and work through these problems. I think that I will do a follow-up lecture with a problem session as opposed to moving on to the next section. So the next lecture on Thursday will likely just be a problem session to follow this up, just to help you guys get over this new material. Okay. All right.